In this video, we're going to talk about how to take the derivative of a trigonometric function. So we're going to start by looking at the function sine. So we're going to let f of x be sine of x. Now, if you recall what the graph of sine of x looks like, it has this wave-like nature to it, which just kind of repeats, oscillating between 1 and -1. And now a function that is somewhat similar in nature is cosine. Cosine's graph looks like the following. And so it also goes between 1 and -1. But if we pay attention to tangent lines, you'll notice that we have a horizontal tangent line here, and that corresponds to a point of 0 here. And each time where cosine has a horizontal tangent line, it looks like cosine is 0. And so this kind of hints that there's some connection between the graph of the derivative of sine of x and the graph of cosine of x. And we're going to see that as we compute the derivative of sine. So if we want to find the derivative of sine, we're going to have f prime of x is the limit as h goes to 0 of f of x plus h minus f of x divided by h. Plugging sine in, this is the limit as h goes to 0 of sine of x plus h minus sine of x, all divided by h. And so now we're going to use a trig property on sine of x plus h. And so sine of x plus h is sine of x cosine of h plus sine of h cosine of x. That's just a trig property, and so we're going to use that trig property now to get the limit as h goes to 0 of sine of x cosine of h plus sine of h cosine of x minus sine of x, all divided by h. So at this point, we're going to split this limit up into pieces. This is the limit as h goes to 0. And now we're going to group everything that's got a sine of x together to start with. So we're going to have sine of x cosine of h minus sine of x, all divided by h. And then plus sine of h cosine of x divided by h. And so this then is going to be equal to the limit as h goes to 0 of sine of x cosine of h minus sine of x divided by h plus the limit as h goes to 0 of sine of h cosine of x divided by h. So at this point, what we're going to do is we're going to pull out the things that have x in it. The limit only is caring about what h is doing, so as far as h is concerned, x is a constant. So this first limit becomes sine of x times the limit as h goes to 0. And I divided sine of x off of each term, so I have cosine of h minus 1 divided by h, and plus cosine of x times the limit as h goes to 0 of sine of h divided by h. So now we just need to compute these two limits. We need to know what this piece becomes, and we need to know what this piece becomes. And so we're going to actually do that in another video, so I'm just going to tell you what these limits are. They're not easy limits to compute, but we will compute them in a future video. So the limit as h goes to 0 of cosine of h minus 1 over h is 0, and the limit as h goes to 0 of sine of h over h is 1. And again, we will justify that later. And so this then gives us sine of x times 0 plus cosine of x times 1. So we're left with just cosine of x. So what we found then is that the derivative of sine of x is cosine of x. And so we've computed the derivative of sine up to those two limits. And now it turns out that if you do almost the exact same process with cosine, you would get that the derivative is negative sine of x. So we're not going to justify that one, but the process is exactly the same as what we just did. And you even get the same two limits of cosine of h minus 1 over h and sine of h over h showing up. So let's do some examples of computing derivatives now that we know the derivative of sine and the derivative of cosine. So first, we want to differentiate y equals x sine of x plus 2x. So we want the derivative here, so we want dy over dx. So this is going to be the derivative with respect to x of x sine of x plus 2x. We can break up over addition to get the derivative of x sine of x plus the derivative of 2x. And now for the derivative of x sine of x, we are going to use the product rule. So we have the derivative of x times sine of x plus x times the derivative of sine of x. And then the derivative of 2x is just 2. So the derivative of x is 1, so we're going to get sine of x plus x times the derivative of sine we just saw was cosine, and then plus 2. And so we've just computed the derivative of x sine of x plus 2x is equal to sine of x plus x cosine of x plus 2. So next, we want to find the derivative of tangent of x. And so this is just an application of sine and cosine, because as you might recall, we know that tangent of x is sine of x divided by cosine of x. And we know the derivative of both sine and cosine, and so to compute the derivative of tangent, we're just going to use the quotient rule on sine over cosine. So the derivative of tangent of x is the derivative sine of x over cosine of x. And by the quotient rule, this is the derivative of sine of x times cosine of x minus the top, which is sine of x, times the derivative of the bottom, which is cosine of x, all divided by the bottom, which is cosine of x squared. So we're going to compute these derivatives now. So the derivative of sine is cosine, so we're going to get cosine squared of x, because we have cosine times cosine, minus sine of x times the derivative of cosine is minus sine of x, all divided by cosine squared of x, which equals cosine squared of x. Then we've got a negative sine squared, so we're going to have positive sine squared of x. For the second term, divided by cosine squared of x. Now, a trig identity says that sine squared plus cosine squared equals 1. So this is just 1 over cosine squared of x, which is secant squared of x. And so that is then our derivative. The derivative of tangent of x is just secant squared of x. Okay, so that's how we take the derivative of tangent. But we can actually do this process to find the derivative of all of the trig functions, because all of them can be written in terms of quotients with sine and cosine. And so just the quotient rule with knowing the derivative of sine and cosine gives us the derivatives of all 6 of them. And just for your benefit, we're going to write down all of them. So the derivative of sine, we already mentioned, is cosine of x. The derivative of tangent of x, we just saw was secant squared of x. Skipped cosine. The derivative of cosine is negative sine of x. The derivative of cotangent of x is going to be negative cosecant squared of x. Then the derivative of secant of x is secant of x times tangent of x. And the derivative of cosecant of x is negative cosecant of x times cotangent of x. And so these are the derivatives of the 6 trig functions. Now I wrote them in this pattern on purpose. So all of these are the co-functions, like cosine, cotangent, cosecant. And notice all of these have a negative. So the derivative has a negative for the co-functions. And it's positive for the non-co-functions. So that can kind of help you keep track of your sign of if you should have a positive or negative. And again, all 6 of these, well, all 4 of them other than sine and cosine, come from just knowing the derivatives of sine and cosine. So now that we have those 6 derivatives, let's look at another example. And so we want to find the values of x, where f of x equals secant of x divided by 1 plus tangent of x has a horizontal tangent line. So we want to find where this function has a horizontal tangent line. So in other words, horizontal tangent lines are places where the tangent line has a slope of 0. So really what we're saying here is we want to find all values x where f prime of x equals 0. So that's what we're really asking here, to find all horizontal tangent lines. And so we need to take the derivative. So we have the derivative of f. And using the quotient rule, it's going to be the derivative of secant of x times 1 plus tangent of x minus secant of x times the derivative of 1 plus tangent of x, all divided by 1 plus tangent of x squared. And so this is just applying the quotient rule. So now let's compute each of these derivatives. So the derivative of secant is secant times tangent. So we have secant of x times tangent of x times 1 plus tangent of x, and then minus secant of x times the derivative of 1 plus tangent of x. The derivative of 1 is 0. The derivative of tangent is secant squared. And this is all divided by 1 plus tangent of x, all squared. And so now notice that we have a secant multiplying everything on the top. And so we're going to factor secant out of that whole expression. And so to see that, this is going to be secant of x times, and then distributing through, we have tangent of x plus tangent squared of x. So this is just distributing that tangent through, and then minus a secant squared of x, all divided by 1 plus tangent of x squared. And so now, using another trig identity, we have that tangent squared minus secant squared is -1. And so this trig identity comes from the Pythagorean identity of sine squared plus cosine squared equals 1. You just divide everything by cosine squared and then rearrange. But why that matters to us is this then becomes secant of x times tangent of x minus 1. All divided by 1 plus tangent of x squared. And so this is our derivative of f. But the question we were interested in was when we have horizontal tangent lines. So we want to know when is this expression equal to 0. So in other words, when does 0 equal secant of x times tangent of x minus 1 divided by 1 plus tangent of x all squared. And so that's what we were really interested in. And so we've got 0 equals secant of x times tangent of x minus 1 over 1 plus tangent of x all squared. Now, for this expression to be 0, the top needs to be 0. And so we must have the secant of x times tangent of x minus 1 equals 0. Now, for a product of two things to be 0, one of them must be 0. So either secant of x equals 0 or tangent of x minus 1 equals 0. Secant, however, is never 0, so this never happens. And the easy way to see that is secant is 1 over cosine, and 1 over cosine is never going to be equal to 0, because the numerator in that case is always 1. And so we really are just in this situation of tangent minus 1 equals 0. So we want to know when is tangent equal to 1. And tangent is equal to 1 occurs at pi fourths and multiples of pi, and integer add-ons of pi fourths. And so tangent of x equals 1 when x equals pi over 4, because that's when sine equals cosine, plus if we add on any integer multiple of pi. And so this is just using the periodic nature of sine and cosine. So every time you rotate by pi, sine and cosine are both going to have the same value, so tangent is going to be 1. And so what we have found then is there are horizontal tangent lines for the graph of f of x equals secant of x divided by 1 plus tangent of x for each x equal to pi over 4 plus n pi for any integer n.